Okay, now let's look at how can we solve a simple problem using conjugate beam method. So here we have a beam which is loaded with a 8 kilonewton load here and a 4 kilonewton load here, and it has a E value 200 gigapascal, that is Young's modulus, and stiffness or second moment of area of 17 to 10 to the 6 millimeters to the 4. Now we have to plot a conjugate beam. Before plotting a conjugate beam, it is good if we can obtain bending moment diagram to this beam. So let us work out how to do this one. So now let me plot let me plot this beam. Let me plot a beam, yeah. And here I have two reactions because it's a pin, and I have one reaction, it's a roller, and there is a load that is 8 kilonewton, and there's another load 4 kilonewton. So now this distance is 3 meters, and this is 3 meters, and this one is 3 meters. Okay, my one is not in the ratio, but I understand that you get the bigger picture of this problem. So now I need to find these reactions. So this is RA, RB, and this is HA. So if I take equilibrium in the horizontal direction, sum of all the forces is equal to 0. That brings me HA to 0. Then if I take the equilibrium of all the vertical forces, Fi is 0, which means, okay, this is my first equation, and the second equation I'm going to derive now, that is RA plus RB minus minus 8 minus 4 is equal to 0. So RA plus RB is equal to 12 kilonewton. So this is my second equation. Now I think we need one more equation to solve this problem. So what I'm going to do is I'm going to take moment by A. So my sign convention is always counterclockwise positive. So I'm going to take moment by A, which means RB into 6 minus 8 into 3 minus 4 into 9 is equal to 0. So that is 3 cancels off, and 2, and again 2, 4, 2. So RB becomes 4 plus 6, 10. So RB is so 2 into 3, 6, and here is 4 into 1, 4, 10 kilonewton, and RA is 2 kilonewton. So that gets me the reactions. Now I need to plot the bending moment diagram, so I'm going to go through how can we plot this as a full process. I'm not going to just draw the bending moment diagram because this is the first example we are doing using conjugate beam. So now if you look at this beam, we need to derive a set of equations that can provide me sort of a relationship between the bending moment diagram and the distance. Because say if you consider a section between A and D, that is a typical section where we have only one external load at A. Now if you look at a typical section between D and B, then in that section there are two forces acting. One is the reaction at A, and another one is 8 kilonewton. And if I take another section at C, between B and C, then that gives me, that has about 3 forces acting in that typical section. So this is why we need to obtain 3 different sections. So if I consider section 1, which is x greater than 0 less than 3, now that looks like something like this. So RA is 2 kilonewton, and the distance at some x distance I'm going to mark mx. So actually there are further 2 more unknowns. The other one is Vx and Ax. So this is a typical section, and this section is in equilibrium because the beam is in equilibrium. So if I again derive equilibrium conditions, I'm not going to derive equilibrium conditions for shear force and axial force, and we know axial force is 0 and shear force can be obtained. Now I am interested in moment because I need to plot bending moment diagram to plot M over EI diagram. So now if I consider equilibrium condition, and if I take counterclockwise positive, so mx minus 2x is equal to 0. So mx is equal to 2x. So this equation is valid between 0 and 3. So that is means that this means it's a linear equation, linear curve where the moment is increasing with the distance. Now if I consider the section 2, then that section is a typical section where you have the RA, that is 210, and you have a load that is acting. That load is 8 kilonewton. So now this is for the range x greater than 3 less than 6. So now the mx, and the x is always obtained from the support, left hand support. So plus, now mx minus 2x plus 8 into x minus 3, because this is 3. So that is equal to 0. So now this gets me mx is equal to 2x minus 8x plus 24. That is 24 minus 6x. This is my 5th equation. So now I have a formula or a relationship between for the range 0 to 3 and 3 to 6. Now I'm going to get the section 3, so which is x greater than 3, sorry, x greater than 6 less than 9. So that will get me the third relationship that I can use to obtain the bending moment diagram. So now in that section, that if you consider that range, a typical section would look like this: 2, 8, and then you have 10. This is 3, this is 3 meters, 3 meters. So here if I consider mx, x is always from the left hand support, so plus mx minus 2x plus 8 into x minus 3 and minus 10 into x minus 6 is 0. So mx is equal to 2x minus 8x plus 24 plus 10x minus 60. So that is 10, 12x minus 4, 8x, 4x, then 24 minus 60 is minus 36. So this is the not the third equation, but the sixth equation, and that is applicable for the region 6 to 9 meters. So now I have three equations, that is equation 4, equation 5 and equation 6. These three equations can clearly help me to plot the bending moment diagram for the entire beam. So if I plot the bending moment diagram, so that looks something like this. Say I hope it's okay. This is 0, this is 3, this is 6, and this is 9. Between 0 to 3 the equation is 2x. So if you substitute x is equal to 0, it's 0. If you substitute x is equal to 3, it is 6. So it's a linear curve. Okay, so linear curve of 6 kilonewton meter. Okay, kilonewton meter. Between 3 to 6, this equation is valid, equation 5. So if you substitute 3 here, then you get 6. Then if you substitute 6 here, it's 24 minus 36, that is minus 12. Minus 12 kilonewton meter. So that is the 24 minus 36. So if let me draw. I think the drawing on this tablet is a bit challenging. Okay, but I try to. It's a linear curve. Okay, so something like that. Then if you substitute for the 6 to 9, this equation is valid, the equation 6. So if you substitute 6 here, then 24 minus 36 minus 12. If you substitute 9 here, 36 minus 36, 0. So it's again another linear curve. So this is the bending moment diagram for the beam. Bending now if I want to plot M over E diagram, so I have to divide all the values by EI. So since EI is constant, I can draw 0, 3, 6 and 9. At 3 it is 6 over EI, and here it is minus 12 over EI, and I have the same graph. Okay, same graph. Now this is a M over EI diagram. Now if I convert my actual beam to a conjugate beam, then this will be the load that I'll be applying on that beam. So now I need to convert my beam to a conjugate beam. So we know that if a pin support in a real beam will be a pin support in a conjugate beam. If it is a internal roller support in a real beam, it will be a hinge in a conjugate beam. If it is a free end in a real beam, it will be a fixed end in a conjugate beam. The reason is at point A you can have deflection, you cannot have deflection, and you can have slope. So slope corresponds to shear force and deflection corresponds to bending moment. So in the conjugate beam at A you can have shear force, but you cannot have bending moment. So if you want a support that can be exposed or can carry shear force but not bending moment, then it should be a pin support. Then if you consider the point B where it's a roller in the real beam, which means at that point there can be some slope, but there cannot be any deflection. So if you compare with the conjugate beam, you can have shear force, but you cannot have bending moment. So if you want to have shear force and not bending moment in the middle or somewhere inside a beam, then there should be a hinge. So a hinge support can carry shear force, but it cannot carry bending moment. If you consider point C in the real beam, that can have deflection and that can have slope, means in the conjugate beam there can be shear force and there can be bending moment, so it should be a fixed support. So if I draw the conjugate beam, okay, so this is my conjugate beam. Okay, conjugate beam. So here 0, 3, 6, 9. So at 0 it's a pin. So there are two reactions. Okay, it's a pin, and here it's a hinge. Okay, a pin, a hinge, and here it's a fixed support. So it's a beam which has a segment 0 to 6. It's a kind of a simple support, and then here it's a cantilever. So there's a hinge, there's a fixed support, fixed. So now this is the beam, and I'm going to have my load, that is M over EI diagram is going to be the load, 6 over EI, then here 12 over EI, so that is so I'm not marking minus 12 over EI. The reason is, now when it comes to a load, we are applying in that direction. So this is the, if it's a positive load, it acts upward. If it's a negative load, it acts downward. Okay, so now this is the conjugate beam. So if you consider this conjugate beam, what we can do is, here there are 2 reactions here, 3 reactions here, so it looks like we can't solve this, but one thing we can do is we can break at this point B. You can break the beam at point B because there's no moment at point B, so you can break it at point B and convert them into 2 sections, and then you can find relevant equations for shear force and bending moment. So now my question is, we need to find slope and displacement at the NC of the beam. So what we need to find is, we need to find slope and deflection at C, at NC. Means that if I find the shear force and bending moment at this point C, that's enough. Okay, so let's do that one. I'm going to shift this question a little bit down because I need more space to solve this problem. So because this is the second problem we are going to look at, so now let me move this. Okay, that's good. So now if I consider the section BC, okay, so if we break into 2 sections, okay, so that is, first section is A to B, Okay, so here you have a pin support, and here we can consider it's a roller because it's a hinge, and I'm breaking here. So this is my load acting on that section, so that is the load. Okay, so here we have, this is A, RA, HA, and here RB. Okay, so now we can solve this one and find RB, and then now if you take the next section, then you have here, you have RC and you have MC, because, and you have AC, and here you have an equal and opposite RB and the load which is acting on the beam. So we need to find RC and MC, because RC is equal to shear force at point C and MC is the bending moment at C. So now to do that I need RB. So I need to solve this section part 1, part 2. So I need to solve part 1 to get RB, then I can do part 2. Okay.